Hey guys, so in this video we're going to be talking more about the Fourier transformation that we came up with in the last video, but first I've got a few quick things to talk about before we do that. So the first one is a little change in notation, and I did this intentionally, but from this video on we're going to be using a slightly different notation. For the material in the previous videos, this first notation that I've been using is I view as a lot more helpful and a lot less confusing. The notation we're going to be using from now on is first of all more helpful for sort of visualizing the material in this video, but also is the more standard notation, the more standard convention to use in quantum physics. I'll show you in a minute why I had used the less standard notation at first. But so first of all, the notation is that thing that we used to call A being that definite position, we are now going to be calling x naught, x sub 0, which hopefully you know from physics and math classes, we say this is x naught. And what we used as B, especially in that last video, sorry, that was a bad arrow, is as B in that last video, we are now going to call k naught, right, which is that definite value of k. And so, for example, that thing that we used to have phi sub a of x is delta of x minus a, right? We're now going to say phi sub x naught of x is delta of x minus x naught, right? This is just the wave function of x. X is the variable, x is position in general. X naught is that specific value of position, right? And so this is the wave function with a definite position, x naught. Same thing, we had phi tilde sub b of k, right? And this will now, this was delta of k minus b. Now we're just going to say phi tilde sub k naught of k is delta of k minus k naught. Right, and the reason that I used this A and B notation in the previous videos is we had to write integrals like this, where we wrote psi of x is the integral from negative infinity to infinity of we had ca phi sub a of x dA. And otherwise, we'd have to write it like this. Psi of x equals the integral from negative infinity to infinity. C sub x naught phi sub x naught of x dx naught. And this, I think, is a lot more complicated and a lot harder to see. That this is a function of x naught. We're integrating over x naught. This is a function of x naught and x, and the answer at the end will be a function of x. It's a lot easier to see when we write it like this. Conceptually, too, I think it just makes a little bit more sense when you're doing this kind of notation. Especially when you have the dx naught, it just does not look very nice to deal with. But from now on, we're not really going to have to write things like this. We've sort of done everything we can do with this kind of, integral. We figured out what cx naught is. We figured out that's like psi of x naught. We figured out this was the direct delta. We're going to be sort of taking this and expanding on it. We're not going to be writing integrals like this so much anymore. So I'm switching to the more standard convention. So I'll erase that, hopefully you have it down, if not, go back, and you can write it down if you need to. And so the other thing, before we get to the Fourier transformations, is talking a little bit about our Dirac orthonormality condition, right, which, 2 videos ago, I believe 2 videos ago, we had established our Dirac orthonormality condition that said that if I have let's see, we had phi sub q1 inner product with phi sub q2. This gave us the delta function, delta of q2 minus q1, or delta of q1 minus q2, either way. Right? This was our Dirac orthonormality condition for our continuous Hilbert space, or function space. And we have now a few things. Well, we found that phi of x naught, right, of x is delta of x minus x naught, right? We found we know that phi sub, I'll say k naught will be our definite value of k of x, right, is 1 over root 2 pi e to the I k naught x. And again, this is a little bit different how I was writing it before. Before I was a little bit lazy with it. I said phi sub k of x, where k was our definite value of k. But now I wanna just make sure we're clear that, you know, if it has a subscript k sub 0, k naught is our definite value of k. It's not the variable k. When I just write it e to the I k x, you don't know, is x the variable, is k the variable. Here, k is some particular value of the wave number, x is the variable, right? And we also know in k-space, we know that phi sub x naught tilde of k, right? We know that this is 1 over root 2 pi e to the minus I k x naught. Again, you see here in this notation, it shows a lot better. Some particular position x, k is our variable. And then phi sub k naught of k in the momentum basis is delta of k minus k naught. Right? And I'm not going to show explicitly that all of these follow our Dirac orthonormality condition. You guys can, I'll leave a few of them for you guys to do. But I want to do at least these first two, right? So plugging them into this condition, I want to make sure they follow our condition, right? So if we take this first one, the inner product we're taking is the inner product of delta. Oh, that was not good. Delta of x minus x naught, inner product with, or sorry, not x naught, x1, right? And inner product with delta of x minus x2, right? Again, x1 and x2, just like how we had a few videos ago, those are also specific values of the observable x of the position, right? And so when we do this, we can expand this into an integral. We take the complex conjugate of the first, but the Dirac delta function, it's a real function. We don't have to take its complex. Well, if we take its complex conjugate, we'll just get itself because it's real. Right? So this is delta of x minus x1, delta of x minus x2 dx. And we are now going to use the trick that we have used so many times with the Dirac delta function. What we can see is that this thing, the whole integrand here, will be 0 if x does not equal to x2, or we could do if x is not x1, but I'll just take this one. This Dirac delta will be 0 if x is not x2, right? So I can actually change this x to an x2 and bring it outside the integral, right? And so then we'll get, I'll put this back in green. Then we'll get delta of x minus x2 minus x1 not a good 2, but you get the point, times the integral from negative infinity to infinity, delta of x minus x2 dx. Again, this integral is just 1, and we are left with our answer. Delta of x2 minus x1, perfect, right? That's delta of q2 minus q1, where q here is x, right? Because we're taking the inner product of phi sub x1 and inner product with phi sub x2. Okay, so now let's go to the second one. We are now taking the inner product of 1 over root 2 pi e to the I k naught, or k1x, inner product with 1 over root 2 pi e to the I k2x. Right, just to show you again, this is phi sub k1, and this is phi sub k2 of x in the x basis. Okay, so hopefully you have that down. I'm going to erase these just to make this look clean. So I'll go back to our color. Okay, so we put this into an integral. We've got the integral from negative infinity to infinity of 1 over root 2 pi. Again, we're taking the complex conjugate of this. The 1 over root 2 pi can just come out of the complex conjugate. It's real. E to the minus I k1x, because we take the complex conjugate, times 1 over root 2 pi e to the I k2x dx. And now we can do some algebra. Well, 1 over root 2 pi times 1 over root 2 pi is just 1 over 2 pi, right? And that can come out of the integral. So 1 over 2 pi times the integral from negative infinity to infinity of, and then we can combine the exponents. This would be e to the I k2x minus e I k1x, right? This would be e to the minus I, or e to the minus I k2x plus, or k1x, sorry, plus I k2x if we were combining the exponents, and then we could combine this even further to make this e to the I x times k2 minus k1, right? And we take this integral dx. And now this may not look super familiar to you, but this is actually one of the definitions. This can actually be used to define delta of k2 minus k1. This is one of the mathematical definitions of the Dirac delta function. I'm not going to go too far into why this is. I'll have a link in the description that will explain that, why this definition would work. But the big thing that I want to show you, first of all, is why it makes sense that if k2 equals k1, why this thing would be infinite, right? So if k2 equals k1, k2 minus k1 is 0. So it's e to the I x times 0, so that's e to the 0, which is 1, right? So we're taking the integral from negative infinity to infinity, and then multiplying it by 1 over 2 pi, of 1 from negative, right, from negative infinity to infinity. So this is our x-axis. This is the function 1, right? And we're taking this area from negative infinity to infinity. Well, that's obviously infinite, and delta of 0 is infinite. The reason why it's 0, if k2 in k1 are different, I'll leave for the link in the description. Okay. Lastly, I'll have you do the other two on your own if you so choose. But just to outline sort of what you would need to do, it's the same exact, actually the same exact integrals that what we did before. The big thing you need to remember is inner products can be done in the position space, but they can also be done in any other basis. Remember the dot product, like how we had it before, we could do this in any basis. That's why it's so important. So if we're taking the inner product of phi sub x1 tilde of k, inner product with phi sub x2 tilde of k, right? We can do this integral, well, we can't really do this integral in the x basis because we're not given functions of x, right? These are specific values. We're given functions of k. We can do this inner product, this integral, in the k basis, where we have the integral from negative infinity to infinity of phi tilde sub x1 star of k times phi tilde of x2 of k dk. Right, we can do this integral, sum over all possible values of k, right? It's just using in a different basis, a different space, and we can still do this inner product. Hopefully that makes sense. That was one of the main points when we introduced the inner product, that I tried to stress that it can be done in any basis. So go back to look at our videos on the inner product back in section 2 if you need to be reminded of that. Okay, so now back to Fourier transformations. Also, if you plug those in, you'll see that this was just the integral that we just did with the definition of the delta function. So here I have made a table of some important Fourier transformations that I'm going to go over some of these in slightly more depth, and some of them I'm just going to scan over. Here I've written our Fourier transformation. It is important to remember we have this is the Fourier transform. And this here is the inverse Fourier transform. Right, transformation, it's called both. And it has the 1 over root 2 pi normalizing factor. So it's the normalizing factor, and I'll show you where that comes into play. We're not going to be deriving these, although if you would like to try deriving these first two, they are actually just the same integrals that we did earlier in this video, just a few minutes ago. So I'd welcome you to actually try calculating this Fourier transformation, and it is not very difficult at all if you know how to do those integrals that we just did. So this just shows if psi of x is 1 over root 2 pi times e to the I k naught x, we know that this is a wave function with a definite value of k being k naught, right? And in k-space, it would make sense that its Fourier transform is delta of k minus k naught, right? That these are the functions in position space and k-space of a wave function with a definite value of k naught, with the definite value of the wave number being k naught. Right, same thing here, delta of x minus x naught, that is the function with a definite position x naught. And in k-space, it's 1 over root 2 pi e to the minus I k x naught. This is the function in k-space that has a definite value of k, the definite value of x being x naught. Right? Another thing, you guys have heard of the uncertainty principle, that you can't know position and momentum at the same time. You can see that here, right? Because if you, for example, know position exactly, there's only probability at only one single spot. This complex exponential, right, the norm squared is 1, it's the same everywhere. You have no way of knowing whether this particle has a momentum of positive infinity, negative infinity, somewhere in between, right? Same thing here, if you know its momentum for sure with this delta function in the position basis, it could have a position anywhere. You have no idea what its position is, right? If you just think about the probability densities, the probability density here, if you took the norm squared of it, would be, the norm squared of this is 1, so it would be 1 over 2 pi, which is just the same everywhere, right? So you have no idea what momentum, what k it has. Again, if you're taking the probability density in k-space. So now we get into the interesting ones. These are the Gaussians. And Gaussians, I'll sketch a little graph for you guys. Gaussians look like this. Sorry, I'm going to redraw that. I'm not a great artist, especially on this computer. But it is sometimes called a bell-shaped curve, a normal distribution. It asymptotes out to 0, and it's centered around some point, called this point x naught, right? And this would be the function. It's some number, I'll call it capital A, times e to the minus x, e to the minus x naught squared, over 4 sigma squared, and I'll talk about what that means in a second. But so this is what the Gaussian is. It is like a bell-shaped curve, and it shows sort of a normal probability distribution. And I'll get back to the sigma at the end. It will be important. this thing, it essentially tells you how wide the Gaussian is, or how wide the Gaussian is. So if you graph these, it turns out, right, if you have something here where you have and this is our normalization coefficient. This makes sure that normalization works. So the 1 over square root of a times the 4th root of 2 pi. You have e to the minus x squared over 4a squared, which might look something like this. In k-space, turns out the Fourier transform of a Gaussian is also a Gaussian, right? But if this width is very if it's a small width, the k-space Gaussian, sorry, that's not x, that would be k-space Gaussian, again, not drawn well, but would be wider. So I am adding this in to this video just so I can demonstrate the concept better with a graphing calculator. So what I have here is I have graphed right up here, I have graphed a Gaussian e to the negative x squared over 4a squared. Here I've graphed e to the negative a squared x squared. And I know ordinarily these would be in different bases, but I'm graphing them together right now to show you how their widths differ. So if I adjust a, say I have it big, which means that there is a large width in this red Gaussian, right, the 1 over 4a squared, which would, in our example, be a large uncertainty in position. And as I do that, I start getting a very small uncertainty in momentum, right? The width is very small. And again, these are not normalized. I just wanted to show the concept here. If I instead make the width very small, so this would be a very, very definite, not definite, but it's a very well-known position, right? This is a small uncertainty in position. I now have to have a very large uncertainty momentum. So if I have a small uncertainty momentum, I have to have a large uncertainty in position. So these Fourier transforms, because these will, are the not normalized versions, but these are the widths of the Fourier transforms between position and momentum. And so as you can see, as this red one becomes thinner, its Fourier transform with the sort of the widths are reciprocals of each other with maybe an extra factor of 2 that we will see later in this video. So I just wanted to add this in so I can demonstrate the concept better. Right, and so this function, all it's saying is this is a Gaussian centered around x equals 0, right? And it is and it's a shape like this. Then when we transform it, first of all, having this 1 over root 2 pi factor means that when this one is normalized, if we just put it through the Fourier transformation, this is what we get, and it's already normalized for us. We don't have to do any more work. And so this function, if a is really small, the x function will be very narrow, and which would make the k function be very wide, right? Because if this 4 sigma squared part it has to do with its width, right? You see if this one has a very small width, this one would have a very big width, right? If this one's width is 1 over 4, or if this width is 4a squared, this width would be, I think, a squared over 4, right? Or no, this width would be 1 over a squared, right? Depending on how you define the width. Again, we'll get to that in a second. I just want to give you a qualitative understanding of what these are, right? And this works with the uncertainty principle, that if you have a very known position, if the Gaussian looks like this for position, then for momentum, for the wave number, it will look like that. Similarly, if it's very wide for position, it will look narrow for k-space. I know these are horrible drawings, but hopefully you understand the point that I'm trying to get across here. These other ones are just, well, what if we don't want to have this particle having a, position centered around x equals 0, or here, what if we don't want it having a momentum centered around, momentum equals 0? What if, it's most likely to have a momentum of like 5, but it can go off to 6 or go down to 4, right? But not centered at 0. These are centered at 0. This one is a Gaussian centered at some x naught, right? And when we have it here, the only difference in the Fourier transform is a little boost, right? I call this like a boost. It's you add a factor of e to the minus ik x naught, which is a wave function with a definite value of x naught. So what you're doing is you're taking this Gaussian, you're multiplying it by the wave function with a definite position to sort of shift the Gaussian. It's just a cool mathematical thing, so I wanted to include all of these. Same thing down here. These are the functions in position space and momentum space for a Gaussian centered around the position x equals 0 and the momentum k equals 0. I'm not going to go too much into this. I just wanted to show you the tables. We're mainly going to be using these. But note, for all of these, the widths behave the same way. If I have this 1 over 4a on is the coefficient to the x squared, no matter what, if it's shifted or not, the coefficient that goes with the width is a squared, right? So the widths are inversely proportional, right? Now, previously I said that we had a Gaussian, right? It had the form e to the minus some constant times e to the minus x squared over 4 sigma squared, right? Or I'll say 4 sigma x squared. Or we could have e to the minus k squared, and this could be x minus x naught, whatever, over 4 sigma k squared. So this sigma, the standard deviation, is a measurement of uncertainty, right? And so I'm going to draw this out here in, say, orange. If I've got a Gaussian, right, centered around some point, right? We could have had x minus x naught, quantity squared, whatever. I'll call this x naught, but this will work with k as well. This will have some width at some point, and you could pick this point special, right? So that this is x naught plus sigma x, and this was x naught minus sigma x. And it is chosen so that and this number comes from, actually, I believe it has to do with the number e, actually. Inside of this, you have about 68%. So there's a 68% chance that your measurement will come within one standard deviation, right? It will either be within sigma to the right or sigma to the left of x naught, right? So a higher sigma means this will go out. That means the width is bigger. That means there's more uncertainty. A lower sigma, if sigma were like around here and this were really thin, right? This would be something, for example, with a much lower standard deviation, because you would only have, within like this, you would have a betal, right? So it would be a lower standard deviation, having 68% of the area. And so this, right, this is a measurement of uncertainty. This is actually the measurement of uncertainty, the standard deviation that we use in for the uncertainty principle, if you remember. And so now I want to show you that, in fact, Gaussians are special, that they are the minimum uncertainty wave function. Every wave function, we've already proved the uncertainty principle, and I'll show you actually in a few videos how to get that specific h bar over 2, like sigma x sigma p equal or is greater than or equal to h bar over 2, right? But so specifically, right, we know that there's some minimum uncertainty between knowing the position and knowing the momentum, or knowing the position and knowing the wave number, right? And I'm going to show you here that, in fact, the Gaussian has that minimum uncertainty. So here, if we have, say, and for x, we have in these examples, in all of these examples, we have sigma x equals a, right? And we have, well, we have a squared being equal to 1 over 4 sigma k squared. Right, if we just sort of match this up with this, we see that a squared is equal to 1 over 4 sigma k squared, which means that sigma k, if we do the algebra, sigma k equals, right, we just multiply by this, multiply by sigma k squared, divide by a squared, take the square root, we got 1 over 2a, right? And so sigma x, sigma k, is equal to a times 1 over 2a, which is 1/2. Also note when we see this, if a is big, x is very uncertain, sigma k is 1 over 2a, which will be very small. So if you have a big uncertainty in x, you have a small uncertainty in k, right? And that would make sense with our idea of the uncertainty principle. So sigma x, sigma k equals 1/2. And now the last step, to get this in terms of momentum, well, if we have, say, a momentum centered around, first of all, let's write, and I'm gonna erase some of this on top so I have a little bit more room to write this, so hopefully you have this all down. Actually, this should just be a review from the last video. Right, we know that k equals p over h bar. Right, that's from our de Broglie relations, right? And so if I know that I've got, a momentum 68% of the time between, say, p equals 3h bar and p equals 5h bar, right? Then we know that, our expected value of p, our center value of p, I'll call it p naught. P naught would be 4h bar, right? And sigma p would be h bar, right? It's 68% chance of being within 1 h bar of the most likely, the average, right? This is the expected value of momentum. Hopefully you kind of see that. And for this now, if we were looking at k, well, if it's p equals 3h bar, it would be k equals, I'll write this in a different color. It would be k equals 3, right? And so between k equals 3 and k equals 5, right? And so we would know that the expected value of k, which is k naught, that would be 4, and sigma k would be 1, right? It's within 1, 68% chance of being within 1 of our value of k. What this shows, this was sort of just an example to show that just like k equals p over h bar, sigma k equals sigma p over h bar, right? That should make sense, right? If you have sort of some uncertainty in momentum, the uncertainty just gets divided by h bar. You're sort of just scaling the uncertainty, right? Hopefully you can review this definition. This should make sense of why this relationship holds. So now using this, well, we know sigma k, this is sigma x times sigma p over h bar is equal to 1/2. And so now we have sigma x, sigma p is equal to h bar over 2. This is for a Gaussian. Right? And in general, sigma x, sigma p is less than or equal to, so in general, sigma x, sigma p is less than or equal to h bar over 2. Or sorry, it's greater than or equal to h bar over 2. Right? And so we call the Gaussian the minimum uncertainty wave function, or sometimes called the minimum uncertainty wave packet. And we'll talk about the wave packets later. So this was just to show you that the Gaussian actually is the minimum uncertainty wave function, and I'll show you this h bar over 2 with the commutator. As soon as we figure out what the momentum operator is, and the position operator, we'll be able to do that commutator and figure out this h bar over 2. Hopefully you know what I'm talking about there, if you remember our uncertainty principle. Okay, so that is it for this video. I will see you in the next video.